Okay, so just going to run through these kind of quickly here for everybody. First off, I already went and put these functions into my Desmos calculator, but you want to pay attention to the fact that it's telling us that C is the amount, so it's not a rate, which sometimes they give us, but then they're giving me this derivative here as well. So I know I have both of those things. And the first question is find the average number of acres, so we're looking for acres, affected by the invasive species from 0 to 4. So for part A, all they are hoping to see is 1 over 4 minus 0 times the integral from 0 to 4 of C of t dt. And the units on this are going to be acres. Okay, and I'm just going to go right ahead in Desmos. Badoom. And there's the graphs of my functions, but I know I need to do 1/4 the integral from 0 to 4 of C. I used X because Desmos doesn't play nice with T sometimes. But you're getting 2.778 is what they are going to want there, 2.778. All right, for B. Find the time when the instantaneous rate of change of C, that's just a very fancy way, instantaneous rate of change of C is just C prime. Okay, so I need C prime of T. I need to equal the average rate of change of C. Okay, and that would be from over 0 to 4, right? So that has to equal the average rate of change of C, which looks like this. Okay, so I just want to solve that equation. So again, I'm going to go ahead and use Desmos for this, and I'd probably write a little more on my paper in terms of like what I'm finding here, but I need to know what C of 4 is, I need to know what C of 0 is, and I need to set that equal to C prime, which I've already graphed. So I'd probably write these numbers out here on my paper if I were doing this, just so they know I know what I'm doing. So C of 4 is 5.128. And I wouldn't reround that because I need my final answer to be accurate to 3 places. So 5.1280311. We'll do the whole number here. 609 minus C of 0, which is 0 over 4. Okay, and I need to know when are they equal. So I'm going to go ahead and find what that number is. And I wouldn't type in those numbers again. I would just do C of 4 here, which makes it pretty simple. Just like that. And I need to know when is that number going to hit the derivative. So 1.28200779022. Just, I could probably copy this actually and just drop that in. Rather than typing it in again, I know I already typed it in, but I would just drop it in like that. And I don't care about C here, but I do need to see where is this thing going to hit. And you can see it happens right here. Let's make this a little bit bigger. You can see that it's happening right here at 2.154. So we're going to write T equals 2.154. And we want to put some units on there. And we're measuring T in weeks. So we're going to say weeks. Okay. And I'm going to read the question again and make sure I answered everything because I'm doing these for the first time right now today. They just got released. Heard my students talk about it for the last couple of days. So let's see if they thought they were as difficult as they really are here. Find the time when the instantaneous rate of change of C equals the average rate of change over this time. Show the setup. Okay, boom, did all that. So part C, which I'll do over here for us. Let me make this pen a little bit thicker too. Okay, so it says assume the invasive species continues to spread according to the given model for all times greater than 0. Okie dokie. And again, we have that the invasive species of plant appears in a fruit grove and begins to spread. The function models the number of acres that are affected by the species. Okay, so write a limit expression that describes the end behavior of the rate of change in the number of acres affected by this limit. Yeah, I heard a lot about this question. They're like, how, what limit? So this is a little unusual. I haven't seen one like this on the Calc AB test up until this point. But as long as this is going to happen forever, these two functions model what we're looking for here. And it says write a limit expression. So my first bet would be this. that describes the end behavior. And end behavior, we're always talking about going to infinity or negative infinity. It's talking about time here. We're definitely going to infinity. Of the rate of change of the number of acres. Well, that's just C prime. And I had a handful of kids tell me they got this set up like this, which is exactly how you're supposed to do that, kiddos. Nice job. Let's write that a little bit cleaner. Squared. And it equals 0 because the denominator is a t squared and the numerator is a constant. Okay? And that's just to find that, right? Evaluate the limit expression. There you go. So 0. Okay? That's good. And then lastly, at t equals 4, the 4 weeks, after the species appears in the fruit grove, measures are taken to counter the spread. So the function a, which is defined by c minus this fancy looking integral here, models the number of acres affected after 4 to 36. At what time does a attain its maximum? Okay. Anytime they ask you to find a maximum on a closed interval, we want to do a handful of steps. Number 1, so you don't need to write these numbers here, but step 1 is always, if you want to find the maximum, you need to show that I need the derivative of this thing to equal 0. Okay? So I need a prime of t to equal 0 because I'm trying to maximize a. So I need the derivative of a to be 0. So a prime is going, I'm going to write this out, is c prime of t minus, and the derivative of an integral expression here is just, so 0.1, which is a tenth, I'd rather have a fraction in there, times ln. I'm plugging in the top limit, and then technically there should be like a times a 1 here because you got to derive that, and then minus a 0 because we're going to plug 4 in as well. But anyway, you should get this, 1/10 ln of t, and I need that to equal 0. And I don't know what that's going to be, so I got to come back over here to my handy-dandy Desmos. And on here, I'm going to graph c prime of t. I need capital C prime of x, really, minus 1/10 ln x. And I need to see where that's 0. And all this other junk is kind of jumbling up my graph here, so I don't want to see that. Okay. Now, I know it's going to be bigger than 30 or 4 because that's when this thing starts. Okay, so we might zoom out a little bit like this. It's hard to see that. So again, you can play around with these. I just need to see where this thing hits 0. We can say from like -2 to 2. That's going to be a lot better looking for us here. And I can see it's going to happen right here. So I'm going to grab this number here, 11.4417. And I'm going to write the answer, 11.4417. T equals 11.4417. And I'm going to put units on that. That says weeks very sloppily. Okay. But that's not the answer. That's just a possibility. So this is the second step to these questions. Number 1, you show, hey, I know I need the derivative to be 0. Number 2 is you find that number. And then number 3 is, sorry, my phone's going off. I'm very popular. You find the amount at the endpoints. So I need to find a of 4. I need to find a of 36. And I need to find a of 11.4417. And whichever one of these is the biggest is going to be the maximum value. Okay, and what I'm doing is showing that I know the only possible place a max can happen is at an endpoint or at a critical value. So to do this, though, we got to hop on to Desmos again and talk about what A is here. So, and luckily, we can type this right in Desmos. So A of t is just C of t. So I'm going to turn this off here. I don't care about you. So A of t equals, I'll use x here, equals capital C of x for me minus the integral from 4 to x of, I think it was 1/10 ln. I got to do a t in here for this to work out. And it's going to graph it. We don't really need to see the graph of this, but I'm going to double check and make sure that I've entered this in correctly. C minus the integral 4 to x of this thing here, which is what they got. C minus 4 to this 1/10 ln x dx. Okay. So that's what's going on there. And I don't even need to see this graph. I need to see what's happening at 4. I'm going to enter that number in. I need to see what's happening at 36. And I need to see what's happening at this 11.4417 number. Cool. And as expected here, I know I turned the graph of A off, but since A, I mean, you can see what's happening here, but since A really only counts past 4, and A is the amount, you can see just from this graph that the max is right here at this 11.4417. And if we were to graph the derivative, which is this C, you can see that the derivative is green, is going from positive to negative right there. So that's also going to be the maximum because it's the only possibility. A has to go up and then down again. Okay, but you don't want to write all that because it's hard to explain that. You just want to show that you check these endpoints and this value here. So we're going to list out these numbers, which I'm never going to remember all of them. So I'm going to split screen it for us here. You're going to write these out. You're going to say A of 4 is 5.128. A of 36 is 1.743. And A of 11.4417 is 7.317. And that's going to be acres is what this is measured in. Okay, and then I always have my kids write a little sentence, so I'm going to write in a second. But I'm just double checking this. It says, weeks invasive species appear in the fruit grove, measure taken, blah, blah, blah. The function A defines the number of acres affected by the species over this time interval. Okay, at what time does it reach its maximum? Okay, so we want to make sure that it says at what time. So they really want the t value, but I'm going to list both since we got them. So I'm going to type this out because I can, if it would. Let me make this a little bigger. There we go. Come on, OneNote. Do it for me. 22. So you'd say something like the number of infected acres reaches a maximum of 7.317 acres at 11.4417 weeks. Good. And I usually have my kids write, I checked the endpoints and where a prime of t changes from positive to negative, because that's how we check for maximums. Okay, so that is A, B, C, and D of number 1. I hope you're feeling pretty good about that one. I'm going to post 2, 3, 4, 5, 6 in a little bit too.